Welcome everybody to today's Future Leaders in Robotics and AI Celebrating Diversity and Innovation Seminar Series at the Maryland Robotics Center at the University of Maryland College Park. We have two great talks today. The first is by Homanga Bharadhwaj, and Homanga is a final year PhD student at Carnegie Mellon University. His research goal is to develop embodied AI systems capable of helping us in the humdrum of everyday activities within messy rooms, offices, and kitchens in a reliable, compliant, and scalable manner without requiring significant robot-specific data collection and task-specific heuristics. He is a Meta AI Mentorship AIM Fellow and was a visiting researcher at Meta for 2 years during his PhD, before coming to Carnegie Mellon. He obtained a Master of Science from the University of Toronto and a BTech from IIT Kanpur, India. His research has received a Best Paper in Robot Manipulation finalist at ICRA in 2024, the Best Conference Paper Award at ICRA 2024, the Outstanding Presentation Award at NeurOps 23 Robot Learning Workshop, and has been covered by several media outlets like TechCrunch, IEEE Spectrum, and VentureBeat, among others. So we're happy to welcome you here, and if you don't mind taking over the screen share, please go ahead with your presentation.
Okay, thank you. Thanks for the introduction. Hope you can see my screen now.
I may need to stop sharing on my end.
So we can see it. You're good.
Oh, we can see his?
Oh.
Okay.
Okay, cool. Yeah, so I'll just get started. So to begin with, let's take a moment to imagine what the future looks like. So you're happily watching TV, sitting on your couch, and you suddenly crave some coffee. Just think about coffee, you press a button on your couch, and the robot in your kitchen brings you over a nice cup of cappuccino. Now, everything is going great, and you're just about to grab the cup, but you accidentally drop it on the floor, and coffee spills all over. But there's no cause to worry, because the robot in your kitchen has you covered. It quickly comes up and cleans up the floor and makes it sparkling new. Now, all this while you're still on the couch, happily watching TV. Now, this future is great, and I'd certainly like for this future to be true, but one might argue that this future is sort of already here. We do have robots that can clean the floor for us, like this Roomba on the left, and we have robots that can make coffee for us, like this Artley coffee robot in San Francisco on the right. Now, these systems are great and reliable, and hence they're in deployment, but they do come with significant limitations. In particular, they're limited to doing just specific tasks, either cleaning floors or making coffee, and they also require the relative workspace to be somewhat structured. So we're still kind of far from this future I just described, and to really get there, we would need to have common systems that can do not just one task, but multiple tasks, and importantly, do those tasks in natural environments, like in homes, offices, and kitchens. So as humans, we have this remarkable ability of performing tasks in these very natural environments. We can do all sorts of things. And in my talk, I'll show how we can get robots to actually do tasks in these very environments. In particular, I'll show how we can get robotic policies to do multiple tasks with unified models so that we don't need to train separate models for separate tasks. To set the stage for my talk, we want to build a robotic policy that can perform tasks in unseen scenarios, such that it only requires a high-level language specification that the user provides. For example, a language instruction of the form, wipe the table with the orange cloth. This policy should take in this goal instruction and output actions in this scenario such that the task can be solved. This would be robot joint configurations, joint positions, end effector positions, and so on. And importantly, this robot should be able to use the policy for doing not just one task, but multiple tasks, depending on what the user specifies. And it should not require any test time adaptation or practice. So given a new task, the robot should just be able to do it using this policy. So that's the overall framework. And let's quickly look at how some prior work stack up against this framework. So imitation learning, namely end-to-end imitation learning through approaches like behavior cloning have become really popular recently. And the idea actually is pretty old. And it looks like this. So you basically collect demonstrations on a robot. So you can see a person controlling the robot with a joystick. And once you collect sufficient demonstrations, you do standard supervised learning to train this policy. So here, Pi is outputting some actions, which could be robot joint positions or end effector poses, conditioned on the previous observations. So this is standard supervised learning applied to these robotic demonstrations. And what you get is a policy that can be used to perform this task autonomously. And recently, we have seen this framework being very successful. So DeepMind's robot on the top can tie shoelaces using thousands of demonstrations of robotic shoelace tying. And this robot on the bottom here can open doors and cabinet doors in sort of natural environments, which is great. But this framework on its own is limited to performing a single task autonomously. So you collect demonstrations for a task and you can perform that task autonomously. So it's somewhat limiting in that to do a new task, you need to collect new demonstrations and you can't do multiple tasks in one go. So to change this framework a bit, recent works have made this goal condition. So the idea is very similar. You collect demonstrations, but now not just for one task, but for multiple tasks. And you train a policy that conditions not just on the previous observations, but also on this goal specification. This could, for example, be a language goal that tells the robot what task to do now. And industry has really sort of honed in on the space, and there have been several recent works that have scaled up robotic teleoperation data collection. So we have Google's RT1, RT2 systems that spent maybe 1 or 2 years collecting these 135,000 demonstrations. And more recently, we have seen Physical Intelligence, a startup that has collected even more demonstrations and trained very large policies on this very large robot interaction data set. And the success of this should not come as a surprise because it directly ties to the success of deep learning. And to quote Ilya, success is sort of the only possible outcome if you follow this recipe of collecting a lot of domain-specific data and train very large models on the collected data. However, the caveat here applied to robotics is that it is difficult to collect a lot of these diverse robot interaction data sets in natural environments. For example, I would not want someone to come to my home with a robot and teleoperate the robot to collect lots of data in my kitchen for days. But I might want a robot to autonomously help me in doing tasks in my kitchen. So due to this sort of asymmetry in what data can be collected, the successes of these frameworks are still somewhat limited to relatively structured spaces like tabletop manipulation. And to put into perspective some of the more impressive results from startups in the space, for example, to do laundry, you can have a policy that does laundry, but for that, you're required to post-train the policy, which is a form of fine-tuning, using thousands of demonstrations of this particular task. So at that point, you're limited to only performing this task really well, and you require a lot of robotic demonstrations. So to rephrase Ilya's quote, success is the only possible outcome for the tasks that are within the data distribution. So the question that my research really asks is, can we flip this and look at alternate interaction data beyond robotic data that can be useful for informing robotic policy learning? And a very natural source for such data sets is web videos, in particular human videos, where we have lots of videos on YouTube and other web sources of people doing lots of diverse activities in homes and kitchens. So and these videos are, again, in very natural environments because they're collected by people doing everyday activities, and they consist of a lot of diverse tasks. So they exactly fit the bill for this framework that we want to eventually deploy robots in. And as humans, we have a very natural ability of doing this sort of third-person imitation where we learn by observation. So we can observe others do different things and learn them. And that is primarily how children learn as well. However, current robotic systems require hand-holding where someone teleoperates the robot. And the question that my research really gets at is, can we actually do a lot of this observational learning from human videos and only require a limited amount of teleoperated robotic data in order to get generalizable policies? So the key challenge in enabling this research vision is obtaining predictions from web videos that are useful for robotics, because we can't really hope to extract robot actions directly from human videos. And to tackle this challenge, my research has sort of factorized the overall robotic policy into two parts. So instead of doing end-to-end policy learning, I learned two separate models. The first model is a visual interaction plan that is predicting some sort of embodiment agnostic representation of how to perform a particular task. This could, for example, take the form of motion cues about how a scene should change in the future. And the nice thing about this is that we can train this on lots of web video data. And the second module of robot execution only requires a limited amount of robot-specific data in order to condition on the interaction plan and output robotic actions. So because of this factorization, we can leverage lots of web video data for training this overall policy and use only a limited amount of teleoperated robot interaction data. And that is all possible because we have factorized the overall policy into these two parts. Now, what are some examples of these visual interaction plans? So in my work early on, I showed how we can predict future human hand poses to infer how a human will do a particular task. I also predicted hand and object masks in the future, so predict the motion of how the object of interaction should change in the future. And all of these are predictions from web videos where you obtain ground truth through some mechanism and then learn this predictive model that takes in the initial image of a scene and a goal, which can be a goal image here, or it could also be a language instruction. More recently, I've shown how you can get these more embodiment agnostic prediction plans to work. So here the interaction plan is a point track plan. So given the initial image and a goal, I'm predicting how points in the scene should move in order to realize this goal. Here you can see that the points on the book are moving towards the camera and the points on the background are static. And that is ideally what an interaction plan in this scene should look like. And finally, more recently, I have shown how we can leverage off-the-shelf predictive models like video generation models that sort of naturally predict an interaction plan in the form of a generated video. So here, the interaction plan is literally a video of a person doing a particular task, given just the image of a scene and the language instruction that tells the person what to do. Since this is a short talk, I won't dive into too many technical details, and I want to provide sort of a high-level insight into this first approach of point track prediction. The idea is to use lots of web videos and run off-the-shelf tracking on the video. So given the entire video, current point tracking approaches have become really good at doing reconstruction of point tracks, as I'm showing on the left here. So these point tracks give us the ground truth for predicting how the track should evolve in the future. And once you're able to do this prediction, we only require a limited amount of robot-specific data to learn the robot execution model conditioned on the point tracks. So the overall framework begins with using lots of internet videos and extracting the first frame of the video and the last frame. So last frame is a goal frame, and predicting point tracks that look like this. So without having access to the underlying video, we want to predict how points in the scene should move. And to supervise this model, because we have the underlying video during training, we can run off-the-shelf point tracking and learn to predict the locations of the intermediate points. So this is the first step where we can leverage lots of web videos. And to use this model for robotic manipulation, we can learn to infer sort of approximate rigid transforms of the object to be manipulated. So in this particular case, you can see that the points on the jug are moving and the points on the background are static. So we can try to infer the rotation and translation that explains the motion of all the points at each time step. So this is called the PNP problem, and that gives you an approximate trajectory of how the robot should move after grasping the object. It should namely move as per the rotations and translations that explain the motion of all the points. So here you might have noticed that we are just doing point track prediction on 2D videos. And for robotic deployment, we just use a depth camera on the robot. So you don't need to do 3D predictions from web videos, which is a nice property to have. Finally, we can refine this sort of coarse open loop plan that we have obtained into robotic actions, incorporating the closed loop nature of a residual policy. So the residual policy would correct the approximate open loop actions at each time step, and it'll take in the current observations and learn some corrective behaviors, in particular how to grasp the object and how exactly to move the end effector afterwards. So to do this, we typically use a limited amount of robot-specific data. So in all of this work, the main aim is to generalize beyond the limited robot interaction data that we collect, because we're leveraging lots of web videos. So how exactly do we quantify generalization? And this is a question that's fairly open in robotics, and my research tries to sort of ground this in a certain way. So these are not meant to be prescriptive, but just a way of categorizing generalization depending on what is unseen. So mild generalization is basically unseen configurations of scene object instances and minor variations in the scene, like lighting changes and so on. Then we have standard generalization that corresponds to unseen object instances. For example, we may have seen how to close a drawer, but we haven't seen how to close a drawer of this particular instance, and we want to generalize to this new instance of a drawer being closed. Then you have compositional generalization, where you may have seen the task of opening in the context of an object like fridge, and you may have seen how to close a drawer, but you haven't seen this combination of opening in the context of a drawer. So you want to generalize to this new combination of opening in the context of a drawer. Then finally, we have type generalization, where you bring in unseen object types. For example, an object of the type microwave has never been seen, and you want to generalize to this new object type microwave. So that's the overall idea. And here are just some examples of what the robot executions and point track predictions look like. So all of these are unseen object types. And you can see that the point track predictions here are very plausible. They correspond to the object moving based on what the goal image is showing. And the robot execution is successful in performing the task conditioned on the point track predictions. Then we have other examples of more diverse tasks like pouring from a cup, picking and placing an object, and opening a door. Again, you can see that the point track predictions are very plausible, and the robot executions are successful in completing the task by following the point track predictions. And we've deployed this across a lot of diverse kitchen scenarios and office scenes on the Spot robot. And here's a glimpse of the overall capabilities of this framework. So all of this is with a single policy that is conditioned on different goals. That is what each of the grid is showing here. And to do these executions, we basically move the robot around these natural kitchen and office scenes and ask it to manipulate different objects that naturally exist in these scenarios. So I'll skip this video. And I want to highlight that since we released this work several months ago, it has received a lot of impact in the community. And there has been significant follow-up works that have explored different ways of using point track predictions for manipulation, all with the aim of leveraging cross-embodiment human video data and data sets of other robotic embodiments beyond the specific robot that you want to use. So this is a very neat framework for doing predictions in. So that was about the point track prediction work. And I want to quickly highlight this other interaction plan, namely a video generation plan. So point tracks give you nice motion cues, but they lack the context around the scene. And video generation recently has become really good. So we asked this question, why not try to generate a human video that shows how to perform a task in a particular scene? So that's the overall idea of this second work called Gen2Act, where video models currently are pretty good in maintaining physical realism of the scene and in doing what the language instruction asks the video model to do. So we used the video model zero shot without any fine-tuning and deployed it for robotic manipulation. And the nice thing about generating a video is that we can also extract point tracks on top of it and leverage all the benefits of the previous work that I showed. So the approach is pretty simple. We collect a bunch of robot interaction data, and we do zero-shot video prediction to obtain a video of how a human will do the task corresponding to the robot demonstration. So this gives us sort of free paired data. Given robot demonstrations, we obtain some human videos. And all of this is zero-shot video prediction. Then we can extract point tracks from both of these robot demonstrations and human videos and train a policy conditioned on the generated video using the point track information to output robot actions. So all of this is for training. For evaluation at test time, it's fairly simple. We just move the robot to a particular scene, and we give a language instruction, and we imagine how a human will do the task. So this is zero-shot human video generation, given this language instruction and this image of a scene. Then taking that as input, the policy outputs robot actions, and we train the policy to output actions based on a generated video. So the policy can generalize to scenarios beyond the robot interaction data because the video model works zero-shot in diverse scenarios, and the robot execution is able to successfully follow it. So here is a very sort of high-level glimpse of the results. So given a new scene, we can do zero-shot human video generation, and then robot execution corresponding to the generated videos. And all of these are unseen motion types. So we haven't seen the motion type of pouring. We haven't seen the motion type of wiping on a table. And we can extend this framework to not just single task manipulation, but long horizon manipulation as well by hooking up an off-the-shelf language model. So in order to do a long horizon task, we can ask Gemini what are the different steps involved. It gives us a few different steps. And we do zero-shot video generation for the first step, followed by robot execution, followed by video generation for the next step using the image of the previous execution's last step. So that is what the video on the right is showing here. And we can sort of imagine doing this for very long horizon sequences of tasks across natural environments. So, and here's a glimpse of the overall capabilities of this Gen2Act framework where you deployed it across, again, lots of natural environments in homes and offices and kitchens. So, so that was about this factorized policy approach where we showed how we can get robotic policy learning to really generalize across a lot of diverse scenarios in homes, offices, and kitchens if we have this factorization of training one component of the policy with lots of web data and the other component with just a limited amount of robot interaction. And that brings me to sort of the end of my talk here, where you have seen how to extract all of these motion cues from lots of web videos and learn to predict them. So you watch these videos and you learn to predict how these cues will evolve in the future. And you can also leverage some off-the-shelf predictive models like video generation models in order to infer what to do in a particular scene. And you can also use other predictive models like segmentation models and in-painting for doing semantic augmentations that I did not go into in this particular talk. Now, all of this gave us the ability to act in a lot of diverse environments in homes, offices, and kitchens across multiple robotic embodiments. And importantly, this required only a very little amount of robot-specific data for each of these embodiments. Now, very quickly in the last 2 slides, I want to sort of speculate a bit about the future. So this predictive planning from web data gave us a lot of advances towards this overall vision of performing diverse tasks in natural environments. And going forward, here are just a few directions I'm excited to push this even further. So how can we get dexterous manipulation to go beyond this sort of structured lab-like settings into more natural scenarios like everyday kitchen? So here is Gordon Ramsay chopping onions. So how can we get this sort of slow and structured robot on the left to these natural environments with the same sort of generalization that Gordon Ramsay has? And how can we extend this to not just sort of static manipulation and go beyond that to more long horizon manipulation that maybe requires combining manipulation and navigation? And some of the research questions there are when to move and how to move in order to do a particular long horizon task. And finally, I'm also excited about the potential of these predictive models from web videos beyond robotics, especially to enable embodied applications like in-context action predictions in wearable devices. So you can imagine this being helpful in order to cook a new recipe or assemble new furniture by showing people how to do new tasks beyond helping robots to do new tasks. With that, I'll sort of end my talk by thanking all my collaborators, some of whom I have shown here and many of whom I could not fit in the slide. And I'll be happy to take questions at this point. Thank you.
Thank you very much. You have to satisfy yourself with me clapping, but wonderful talk. We have a few questions for you so far. So, and if anybody else has questions, please put them in the question answer box if you are a typical attendee. And if you are one of the panelists, feel free to put them in the chat box. So Dr. Diaz has a question, which is, is like the human generated video data being vetted, and is it always reliable? What if the video is incorrect or unrealistic? How would that affect performance?
Yeah, so what I did not show here is that we have that point tracks prediction loss as well as part of the policy. So even if there are some artifacts like visual artifacts in the scene and the approximate motion is correct, so video models have these hallucinations where sometimes some object will appear in the scene. So that is taken care of to some extent because we are explicitly learning to infer motion as well through the point track predictions beyond just using the raw visual features. But all of this, you're right, is relying on the video models having some sort of physically plausible generations. And that is true of the video models currently, and that is only getting better. So I think I'm not too worried about video models being physically realistic for these short horizon manipulation tasks. And for the minor sort of defects, we do have additional loss functions in that sort of translation model to go from generated video to robot action that takes care of visual hallucinations. Yeah.
Thank you. I have a question, which is the following. Like some action, well, so I really like the idea of being able to generalize things in different ways. And like generalizing like one drawer or door to another drawer or door seems like very useful. The idea of generalizing actions also seems interesting, but maybe like less well defined or a little more fraught or a little more like art, like in the realm of like kind of art rather not I mean, you're adding science to it, but to me as an uninformed person, it seems like I don't even know how you'd go about doing that. So for example, I'm kind of curious, like the notion of open, even for humans, has like, it's an overloaded word that has kind of multiple different definitions. So we can like, you know, open up a shop is different than opening up a drawer or opening up a door. And at some point, it may not be exactly the same like notion of open. So I guess like, is there space in your framework to kind of deal with that?
Yeah, you're right that language is sort of ambiguous on its own, but in all of these, we do have an image of a scene in addition to the language instruction, right? So I think the language instruction is not, I guess it's not the best way to describe a task, but I think it's the most convenient for humans, right? And that's why we sort of stuck with language instructions. But given an image and the language, so the language is sort of grounded in the context. So I think that makes things a bit more clear. Like when you say open, what does it mean to open when you have a drawer in front of you instead of a shop in front of you, right?
So
I think,
the context kind of starts to matter a lot.
yeah, exactly.
Like, okay,
Yeah,
I guess that makes a lot of sense to me. And it would also be interesting to kind of like back out if you're using human, label data or whatever, like looking
Mhm.
at if there are subsets of open that maybe we're not completely aware of, like as humans, like very different things that to us make sense that they're all open, but like they're kind of different
right.
physically. I
Yeah,
have
yeah, that's true.
a related question, which is kind of, I don't
Yeah.
know, like the contrapositive of that a little bit or something like that,
Uh-huh.
which is like if you're looking at like the point tracks to help determine
Mhm.
some notion of action,
Mhm.
like dragging and opening seem like they would both kind of have like the same large thing getting moved a little bit. So like, how do you then tease that apart? Is it like, have you thought about that?
Um, yeah, I think again it's sort of in the context of for opening, you have a cabinet door, and in the case of opening, you're only articulating a specific portion of the drawer. So I think from context, it's clear that you don't have to move the entire drawer, but you only have to move this particular part of the drawer, and that becomes opening. And then for dragging, you're moving the entire object instead of moving sort of a part of the object. So I think that's how yeah, the policy can disambiguate, but you're right that for both of these, the point tracks would probably visually look similar, and we are relying a bit more on the contextual information, which the policy has access to. So it has access to the RGB observations in the scene as well beyond the point tracks. And I think we're sort of hoping that that will take care of it.
Okay, well, thank you very much. And if there is any other questions, please put them into the question and answer box or into the webinar chat. I'll give you 2 seconds. I don't think that we have any other questions, but thank you very much for your talk. Very great.
Thank you.